Electricity. We all use it. In fact, for most of us, it's become an indispensable and often taken for granted resource. Just imagine how much more difficult it would be to make your morning coffee, communicate with your coworkers, friends, and loved ones, or do just about anything meaningful without it. Electricity is so indispensable that we tolerate the damming up of water supplies to create hydroelectric plants, large farms of wind turbines taking up valuable land, large coal-fueled power plants that belch pollutants into the sky, and even nuclear power plants using large quantities of radioactive uranium and producing waste that we frankly still can't agree on what to do with. But what if there were a different kind of power available? What if humanity could devise a generator the size of a residential home that could power an entire city's electrical needs? Now, what if this incredible technology could use water, the most abundant material at the surface of the Earth, as its fuel, and produce a waste product that simply floats into space instead of potentially contaminating our environment? Sounds like a dream, doesn't it? Usually when something sounds too good to be true, it's because it is. In this case, however, it just might actually be attainable. And if it is, then the path to this technology is nuclear fusion. We just spent a few lectures considering how large nuclei break down to form smaller ones in a quest to become smaller, more stable nuclei with greater binding energies per nucleon. We also observed that iron 56 reaches a sort of a tipping point at which the per nucleon binding energy of nuclei decreases. This, of course, means that if heavier elements tend to break down to lower their energy, smaller ones like hydrogen and helium should have the tendency to want to come together to create larger elements in the same quest. Chemists call this process nuclear fusion. Fusion reactions are the alter ego of fission reactions. They involve the building up of larger nuclei from smaller ones. And a quick glance at our nuclear binding energy chart makes it clear that in most cases, taking two smaller elements and combining them together to make a larger one is an energetically beneficial proposition, right up to element number 26, iron. But of course, there's a catch here. How do you get two atoms to combine with one another? That's asking a lot. As two nuclei approach one another, there's a natural repulsion due to the charges of their nuclei. And we call this force Coulombic repulsion. And to overcome this repulsion and induce two nuclei to come close enough to potentially combine, well, that requires more than a small amount of force. This is why stars are so crucial to the elemental diversity of the universe. Stars like our Sun are the only place in nature that temperatures and pressures are adequate to induce the fusion of atomic nuclei to form new elements. Without stars, our universe would consist of nothing more than hydrogen, helium, and maybe a smattering of lithium. Fortunately for us, there are supermassive stars across the cosmos that have burned for billions of years, smashing atoms together into ever larger and larger elements before exploding in a giant forceful supernova, seeding the universe with heavy elements. Although fusion can theoretically occur between just about any two atoms when the conditions are right, this lecture will be dedicated to the very simplest but most powerful nuclear fusion reaction of all, the fusion of hydrogen atoms to produce helium. This reaction has fueled our Sun for 5 billion years and likely will for at least another 5. But we didn't always know this. In the early 1900s, a debate raged over both the current age and the overall lifespan of the universe, our solar system, and even our own planet. And one of the burning questions was the lifespan of the Sun. Radiometric dating of Earth rocks had put the age of our solar system at about 5 billion years. But possibly an even more important question, how old is our home, would be, how much longer will it last? Now, English astronomer William Huggins had proposed in the late 1800s that the astronomical phenomena known as supernovas were in fact the death of stars not terribly unlike our Sun. So astronomers were beginning to piece together the machinery of the universe, including the somewhat sobering realization that stars had a shelf life, and ours was no different. French astronomer Pierre Janssen had only recently observed the line spectrum of helium in the Sun's corona during an 1868 solar eclipse, revealing that the awesome heat and light generated from our star was released primarily due to the fusion of hydrogen into helium. Arthur Stanley Eddington, a preeminent British physicist and astronomer, famously took up the mantle of determining a prognosis for the sun's lifespan, bringing to bear all that was known about physics and cosmology in his time. And it was Jansen's discovery of helium and the recently discovered mass defect of helium that helped him to complete this puzzle. Eddington famously asserted, if 5% of a sun's mass consists initially of hydrogen atoms, which are gradually combined to form more complex elements, the total heat liberated will more than suffice for our demands. With all due respect to Mr. Eddington, let's put that statement to the test. The nuclear reactions by which helium is produced in the sun are fairly complex, and there's more than one of them, to be honest. But using the mass defect of helium, we can make a pretty good approximation of how much fuel the sun really has in the tank, the way that Eddington did. So here's the calculation that he might have used. Let's answer that question. How much time does our sun have left? So let's assume that the mass of the sun is 1.989 times 10 to the 30th kilograms, a number that's fairly well accepted and fairly easy to calculate based upon the motions of planetary bodies. Cosmologists had this one figured out quite a while ago. Now let's assume, as Eddington did, that 5% of that solar mass is actually fusible material, meaning that at the end of the process we'll have about 5% of the solar mass converted into helium over its entire lifetime. Right? That leads us to 9.945 times 10 to the 31st grams. Notice I've switched that over from kilograms into grams. I'm going to take that value and determine exactly how many helium atoms the sun will make over the course of its entire existence based on these assumptions. So I'm going to have to convert my grams of helium to moles of helium, convert my moles of helium then to atoms of helium, checking my equation for accuracy using my unit analysis tells me that I'm spot on here. This will tell me the total number of atoms of helium in that amount of mass in the sun. And here's our answer. About 1.5 times 10 to the 55 atoms of helium. That is a lot of helium atoms. But we're not done yet. Let's take that number and convert that back into kilograms now so that we can start to work out our mass defect calculation. In this case, my equation will give me kilograms of helium, and I get 7.547 times 10 to the 26th total kilograms. That is the total amount of helium I expect the sun to produce over its entire existence. That energy would then be the mass times c squared. We're back on Einstein's equation here. The total amount of energy that we can expect the sun to put out in its lifetime is 6.79 times 10 to the 43rd joules of energy. That's a staggering amount of energy, isn't it? Now let's assume that there's a steady solar output through its entire lifespan. It's a relatively fair assumption to make. If that's true, we have to ask ourselves, how long does that budget of energy last? Well, we can measure the output of the sun energetically. We simply take the amount that reaches the Earth, right, and then calculate the surface of the sphere at that distance from the sun. We can figure out the total amount of energy that's being radiated by the sun, and that number is about 1.2 times 10 to the 34th joules in a year. Pretty healthy amount of energy, isn't it? So I'm going to insert this into my equation so that joules are going to cancel, and I'm going to get years as my answer. That will give me an estimate of how long the sun can burn. And when I do this, I find about 5.66 times 10 to the 9th years. That's 5.7 billion years. And we know from radiometric dating of the Earth that the solar system formed about 4.5 billion years ago. So using Eddington's estimate, we get about 1 billion years left in the solar fuel tank. Now, in truth, scientists have studied the sun and other stars like it and determined that his estimate was too low. In fact, there's about 9% fusible hydrogen in the sun, and therefore this estimate has been extended to the point where we actually have about 4 or 5 billion years left. So there's no need for you to run out and do any last-minute shopping just yet. So something as simple as the fusion of 4 hydrogen nuclei into a helium atom has created and will create essentially all of the energy that our planet will ever receive from the outside. This energy will be released over billions of years, during which the sun will convert just a minuscule fraction of its mass into energy. Really quite staggering, isn't it? Of course, the whole story of the sun's machinery is much more complicated, But from an energetics standpoint, the fusion of hydrogen to helium is the 800-pound gorilla. Many other nuclear reactions can take place, creating heavier elements up to and including iron. But the primary driver of the Sun's furnace is indisputably this remarkably simple nuclear reaction. The fusion of nuclei is not relegated to processes in deep space, though. Human engineers and scientists have discovered ways to harness fusion reactions like those that take place in the Sun. Of course, the most recognizable of these is what's commonly known as the hydrogen bomb, a device created not long after the historic bombings of Hiroshima and Nagasaki. Now, those bombs used a very different nuclear reaction. The so-called H-bomb finds its roots in a question that Fermi himself posed to another researcher on the Manhattan Project, Edward Teller, in 1941. By then, the design for the gun-type and implosion-type fission devices were pretty well worked out. Even though none had been constructed to that point, confidence was high that the devices would work and generate kiloton yields. But Fermi wasn't satisfied with that. He thought he could do better, using what is a fairly logical progression. If conventional explosives could compress and heat fissile material to the point of a fission explosion, yielding kilotons of force, could a fission reaction create a truly awesome set of pressures and temperatures needed to produce a nuclear fusion reaction in a weapon that would tap the raw power of the Sun itself? Imagine that for a second. A weapon so powerful that Fat Man and Little Boy would serve essentially as a blasting cap for the device. It's a great idea on paper, and Fermi and Teller worked on the idea until the end of the Manhattan Project in 1946. At that point, World War II was over, and the Manhattan Project disbanded with its mission accomplished. But Teller harbored a deep distrust of the Soviets, and even as early as the 1940s expressed his concerns passionately and publicly about this. Being Hungarian-born, he was bearing witness to the slow progression of the Soviet regime into Eastern Europe with a particularly personal slant. Teller remained driven by what he and many others could sense was coming, a protracted power struggle among the victors of the Second Great War. And he believed that superior armament was one of the keys to protecting America's interests. So Teller continued his research with all the fervor that he had when preparing the fission weapons during the Manhattan Project. He would not rest until a weapon based on nuclear fusion was developed. Let's take a moment now and consider some of the reactions that actually do go on inside of the Sun that Teller had hoped to emulate in his new weapon. Now, we always think of nuclear fusion going on in the Sun as hydrogen being fused to make helium. But there are actually quite a number of ways to do this. The very simplest you might imagine is to simply take 4 of those hydrogen atoms and mash them together to create your helium nucleus and 2 positrons in the process. Remember, if we take these protons and have them collide, overcoming Coulombic repulsion, we still have to get rid of 2 units of positive charge to make our helium nucleus. This is in fact one of the nuclear reactions that goes on inside of the Sun. Now, the problem with trying to set off a reaction like this here on Earth, even if you're going to use a nuclear bomb as your blasting cap, is that you can't reach the kinds of pressures and temperatures necessary. This type of reaction doesn't take place at any kind of condition that we could ever hope to generate, even with the deadliest and most powerful of nuclear bombs. But there are other nuclear reactions going on in the Sun. For example, the Sun can do this sometimes in a stepwise fashion. Let's take those 4 protons again and see what I mean by this. Instead of fusing them all at once in a collision of 4 different species, which we know is very rare and very unlikely to have happen, let's instead fuse them to make 2 deuterium, right? Here I have 2 binary collisions instead of a single collision of 4. So this still gives me my positron emission, but it leads me to having deuterium as one of my intermediates in the process. Now again, another binary collision of those 2 deuteriums can take place. And that will give me my helium-4, which the Sun always is after making, and of course release a tremendous amount of energy as nuclear binding energy as well. This gives the Sun an end around to getting over the fact that it's trying to have a quaternary collision up here in this reaction. Down here, it's a series of binary collisions, much, much easier to accomplish at high pressures and temperatures. So Teller wanted to use one of these reactions to release energy in the form of a weapon. So he had the option potentially of using deuterium. And when you fuse deuterium into helium, in his, well, if he were to have used this process, he would get helium and a lot of energy just like the sun. But there's a problem. And again, it comes down to the amount of energy required to overcome the Coulombic repulsion. Deuterium can be made to fuse into helium, but it requires temperatures in the tens of millions of kelvins. And that is too hot to generate, even using nuclear bombs in his day. So instead, Teller turns to a third reaction that goes on inside the sun, one involving the other isotope of hydrogen we haven't discussed yet, tritium. Now, tritium is a little bit more massive than deuterium, and that means that it has a little bit more momentum and is able to overcome the Coulombic repulsion better when it approaches a deuterium nucleus. So he can actually fuse a tritium and deuterium much more easily. It takes about a million or a few million of kelvins to do this, and in the process release a neutron. So this is a bonus here. Not only does it lower the necessary temperatures to the point at which they can actually be created by a nuclear bomb, but it also releases a neutron, which can convert yet another deuterium into tritium, which can perpetuate the reaction. So this is the reaction that Teller used to create the now famous hydrogen bomb. But of course, there are other reactions as well that go on inside of those bombs, but this is the primary reaction that Teller used, and it is indeed one of the reactions that goes on inside of our sun, but just one of many. Teller's research demonstrated that a reaction like this could be used in a weapon capable of producing explosive yields that would make Little Boy look like a firecracker. Here's what he proposed: a weapon in which a primary fission explosion created sufficient heat and pressure to begin the reaction. It forced a plutonium rod into a liquid helium fuel source at temperatures in excess of 4 million Kelvin, all to turn deuterium into helium. The first such device that Teller and his colleagues ultimately helped to create was codenamed Ivy Mike, and it looked more like a factory than a bomb. The device wasn't mobile by any stretch of the imagination, and it was built on the remote island of Elugelab in the Marshall Islands in the South Pacific. In 1952, the Ivy Mike device was detonated, and the power of the stars was unleashed by man for the first time. After the 10-megaton explosion, the island of Elugelab was gone, replaced only by a crater. Engineering developments eventually led to the development of deployable weapons of even greater power, none of which, thankfully, have ever been used. Fast forward about 50 years from our previous discussion. Jensen and Eddington had made great strides in understanding the process of nuclear fusion in our sun, but it took until 1920 and the discovery of the mass defect of helium in Aston's experiment before scientists finally had the idea that fusion of hydrogen might be something that could be achieved here on Earth. It took several decades yet again, and the advent of the Manhattan Project for others like it, for man to finally create a fusion reaction of his own. Of course, the first of these were explosive devices, like Ivy Mike, with uncontrolled fusion being the goal. But the very obvious question remains: can nuclear fusion be not only initiated, but controlled? Could we somehow tap this incredibly powerful reaction the way that Fermi did with fission? It's a tantalizing prospect. Just imagine if we could tap nuclear fusion in a controlled way, not using fission bombs to initiate fusion reactions that are over in less than a second, but more elegantly conducted reaction. One in which hydrogen isotopes are fused into helium and the energy of that process is tapped. We would have power plants that use the most abundant element in the universe as fuel and produce harmless, stable helium as waste that simply floats into space. But the problem that we run into is that even deuterium-tritium fusion, which is the easiest type of fusion reaction to start, requires temperatures about 40 million kelvins to sustain. The energy needed to overcome the Coulombic repulsion of the two hydrogen nuclei is just so monstrous that we can't run fusion in a power plant the way that we can do it in a bomb. There must be something fundamentally different about how a fusion reactor is designed if it's going to be practical for power generation. We have to find a way to run the same nuclear fusion reaction at drastically lower temperatures. We have to create a type of cold fusion. The quest for controlled nuclear fusion started about the same time that the thermonuclear weapon, or H-bomb, research began. Attempts to use magnetic fields to create containment systems capable of generating high pressures have been employed, and physicists call this the pinch technique. Although many of these types of systems have been able to contain high-energy hydrogen isotopes, none can create the conditions right for nuclear fusion. Perhaps the most well-known story of controlled nuclear fusion is the so-called Fleischmann-Pons experiment in 1989. This experiment was a roller coaster ride of emotion for researchers in the field, as it raised the world's hopes for clean, cheap fusion power just before dashing those hopes nearly permanently. In 1989, Martin Fleischmann and Stanley Pons were conducting electrochemical research at the University of Utah, and they believed they were onto something. They had constructed a very simple device that both men believed would change the world. Fleischmann and Pons created an electrochemical half-cell using a platinum electrode submersed in what is known as heavy water, or water containing deuterium instead of hydrogen. Of course, the product of this half reaction is deuterium itself, which should effervesce and bubble out of the system as hydrogen gas. But Fleischmann and Pons had detected deuterium in the platinum electrode itself. Not a particularly surprising claim, since hydrogen gas interacts with platinum very strongly, adhering to its surface. But what they claimed next started a storm of scientific controversy that's the stuff of legend. The two published a paper claiming that they had detected heat in excess of any expected chemical reaction that would go on in their setup. In one of the most famous rushes to press in all of scientific history, Fleischmann and Pons let their excitement and the pressure to patent their potentially world-changing development hurry the publication of their research. Not long after their publication, scientists around the world began trying to duplicate their results. There was just one problem: no one could. Clearly, Fleischmann and Pons had been wrong. The resulting fallout in the professional and popular media was swift and intense. Many popular magazines and newspapers decried the entire situation as a debacle, and both public and institutional support for the concept of cold fusion was crushed. So the work of Fleischmann and Pons is now taught not as an example of nearly making the greatest discovery in the history of mankind, but instead as a cautionary tale of what is known as pathological science. The term used to describe a situation in which a scientist, originally working in good faith using the scientific method, abandons objectivity and gives in to what is known as confirmation bias. To this very day, fusion research is limited in part due to the bitter taste left in all our mouths after the infamous experiment in 1989. But that doesn't mean that humankind will never find a way to harness this awesome reaction. It simply means that we may have to wait a generation or two longer. Who knows? So let's review our discussion on nuclear fusion. We started by reviewing the nuclear binding energy curve, reminding ourselves that most elements lighter than iron can release energy and become more stable by fusing together into larger nuclei. We thought about the concept of Coulombic repulsion and how the key to achieving fusion is to overcome this energetic barrier and bring two nuclei close enough that they can combine and ultimately release energy. Then we talked a bit about the most pervasive example of fusion in our environment, the sun itself. We saw how the detection of helium in the sun's corona by Janssen prompted Stanley Eddington to characterize the reaction that gives our sun its incredible energy output and long lifespan. Then we turned our attention to man's quest to use nuclear fusion for his own purposes. We saw how Fermi and Teller conceived of a device that would release the energy of nuclear fusion in an instant, creating a weapon of unrivaled power. That led us to consider the use of hydrogen isotopes in the fusion process. And we discussed how deuterium and tritium isotopes of hydrogen are critical to making fusion possible under conditions that we can create here on Earth. Finally, we considered the elusive cold fusion technology, the development of which would have an influence on humanity greater than any other, dating back to the discovery of fire itself. But our discussion took a disappointing turn as we learned about the Fleischmann-Pons experiment and the terribly deleterious effect that pathological science can have. In a previous lecture, we considered how the emission of alpha particles and the fission of large nuclei can be used to confirm the synthesis of brand new, supermassive heavy elements. But we didn't discuss how they're really made. And in this case, we can talk about them in terms of nuclear fusion. Now, in order to do this, physicists have to take atoms that otherwise would not fuse together based upon the nuclear binding energy curve and smash them together with such tremendous force that fusion occurs anyway. This is one of the ways in which one of the relatively new additions to the periodic table was obtained. Specifically, I'm talking about the element flerovium, which was first synthesized a few decades ago by bombarding plutonium-244 with atoms of calcium-48 that are moving at about 1/10 the speed of light. This allowed a fusion reaction to take place between the two nuclei. Now, the product of this reaction was a flerovium atom and 3 neutrons. Our task now is to write a nuclear reaction for the entire process and determine exactly what the atomic number of flerovium is and which isotope of flerovium was first synthesized in this now famous experiment. So, let's begin by thinking about the 2 atoms that were smashed together. Calcium-48, which contains 20 protons and has a mass number of 48. And of course, the target, which was smashed into by the calcium, which is plutonium-244, which has an atomic number of 94. Now, when these 2 atoms finally combined to create a single atom of our new element flerovium, 3 neutrons were also emitted during the process. That means in our products here we have to account for the fact that 3 units of atomic mass but no charge were lost from the product before it even formed. So that means that our flerovium atom that was created must have a mass that is equal to calcium's 48 plus plutonium's 244 minus the 3 mass units that were lost in the form of neutrons. And of course, its atomic number, since no protons were lost, is simply the sum of the 20 coming from calcium and the 94 coming from plutonium. So, flerovium, we can calculate from this, is element 114. And the isotope of flerovium that was made in this instance is flerovium-289, because we have to remember that when those neutrons came away from it, they actually removed 3 units of mass from what we might otherwise have calculated. So this was actually the very first isotope of this new element that was ever created, flerovium-289.